we start.
Recording.
Okay, so let's start the next talk. So it is a pleasure for me to present Boyan Sirakov. He's currently full professor of University Pontificia Católica of Rio de Janeiro in Brazil. He works on analysis and application of elliptic and parabolic partial differential equations. Today, his talk will be about elliptic estimates with optimized constraint and application to the qualitative theory of elliptic PDE. So please, thank you for accepting to participate in our seminar, and you can start.
Thank you very much, Anna, and thanks to all the organizers who have invited me to this great conference. It's an honor to be here and a great pleasure. So today I want to tell you a little bit about a few recent results that we obtained together with Philippe Soufflet from Paris-Sorbonne, Université de Paris-Sorbonne. And it's on some classical estimates in the theory of partially elliptic PDEs, such as the Harnack inequality and regularity estimates, in which we search to specify optimal constants in terms of the coefficients of the elliptic operator that appears in an equation, and the size of the domain where it is set, and give some applications. Let me start with the setting. So we take a standard uniformly elliptic second order operator, say in divergence form, in full divergence form, which is the one over here, right? This operator I'm going to call LD as divergence. And let's remember from now on that the letter A will be reserved for the second order coefficients, the letters B will be first order, and C will be zero order coefficient in an equation. We consider weak solutions of such equations, say somewhere of sense. And we assume that the equation is uniformly elliptic with a bounded governing second order matrix. And the coefficients in the equation satisfy the following one of the following classical sets of hypotheses that I've called C0 and C1. C0 is the first order coefficients of key and the zero order and possibly right-hand side of Q over 2 for some Q bigger than n. And C1, it is the A and B1 some Hölder space, and the other coefficients are Q for some Q bigger than n. And it is very classical that under these conditions, under C0, which is obviously much weaker, of course, solutions of such equations as here are locally bounded. And the maximum principle, if there's a coercivity assumption in addition of zero order term, as well as the Harnack inequality for such equations. And if we assume the stronger C1 hypothesis, then solutions actually, they even have continuous gradients. This is classical theory to be found, for instance, in Gilbert chapter. So yeah, we can also consider with the same effect the equations in non-divergence form, at least for the first part of the talk, where we have standard equations. So the usual form, trace of something, plus first order plus zero order, or even some sort of a fully nonlinear equation, which is of Pucci type, such as supremum or infimum or supinf of the operators, provided we set hypotheses which ensure that weak solutions in viscosity sense of such equations satisfy maximum principle and Harnack inequality. Well, so instead of moving immediately to results, let me give some. Let me actually start by describing the open problems that led us to consider optimized estimates. Starting with the following very classical and simple introduction to PDE course result, the strong maximum principle. which says that if we have a subsolution of an equation which touches a supersolution of an equation from below, then they need to coincide. Or speaking of a linear equation here, of course. Or in other words, say we have a non-negative supersolution of a given equation. If it attains a minimum, then it's a constant. All right, let's go. And well, just in a particular case of L, when the operator is Laplacian minus u, this can be seen, for instance, in the following way. You say that if you have a positive function which vanishes somewhere, you cannot put below it the Laplacian of it, right? Apart from the zero function. And in a sense, if we look at this inequality here as in terms of this right-hand side here, u, then we may ask, can we make a little bit, can we assume something bigger than u here and still have the same result? Or in other words, is the strong maximum principle really a purely linear result? Do we have linearity or Lipschitzianity in u here? Well, it's very easy to see that we cannot, for instance, take a power of u on the right. Here, the power has to be smaller than 1, right? So it makes u to the p bigger than u is close to 0. Well, very simple. There is just powers bigger than 2x that violate such equality and non-zero functions. And so, yeah, so somehow this may make us think that this is a linear result, but it's not. I mean, it's nowadays classical result by Vasquez in 1984 that the zero-order dependence it actually may be nonlinear, maybe non-Lipschitz around u equal to 0. And the right hypothesis is the following. Actually, the threshold between here to the right-hand side, u and up, is a function f of u, which is such that 1 over square root of the primitive of that function is has a divergent integral at 0, right? So 1 over square root of the primitive at 0 is divergent. And the standard and main example, I mean, the only type of nonlinearities for this, for which in practice this has been used, is assuming that f is non-Lipschitz, non-linear, but may increase, f of s over s can be no more than log of s to a power smaller or equal than 2 for s close to 0. I mean, under this hypothesis, this is true, this integral hypothesis over here. All right, so that's the main example of for nonlinearity set of u which are non-Lipschitz and for which the strong maximum principle is true. There's been really a very large amount of work on extending the Vasquez maximum principle to weak solutions in various more complex equations than just linear operators, quasi-linear, fully nonlinear equations that are singular or degenerating with respect to the gradient. There's a whole book written by Patricia Pucci and James Serrin, The Maximum Principle, which deals mostly with that question. And well, I'm not going to bother here with proofs because this is a general audience. But the fact is that this result had always been proven by following the classical proof of the strong maximum principle that's usually given in a standard course, which requires a construction of a radial subsolution in some annulus with different values on the two boundaries and non-vanishing normal derivatives. And that actually may be done only if we assume that the operator has bounded coefficients. So previous work would require operators L that have bounded coefficients. And this approach, essentially, which is a ODE approach, does not seem to work with unbounded coefficients. So there were no Vasquez type strong maximum principles for operators with unbounded coefficients. Philippe and I managed to assign to design a different method for attacking this problem that I'm going to talk about, which actually permitted to us to prove it for nonlinearities which are not fully satisfy the Vasquez integral condition, but for all nonlinearities such as in the main example. So all nonlinearities which are such that which are no worse than s log s to the square, we have the results of the super solutions that vanish at one point are identically zero. And non-negative super solutions that vanish at one point identically zero. So yeah, so what is now about the proof itself? So the main ingredient is the weak Kernack inequality that I'm going to recall now, in which we optimize the constant with respect to the domain, to the size of the domain, and the norms of the coefficients of the operator. So let me recall the weak Kernack inequality. This is an extremely classical result too. If we have a non-negative super solution, value of u smaller than zero, in say some domain, then in a compact subdomain, we know that some L epsilon norm, which actually we can go up to n over n minus 2 for the norm here, for the L epsilon norm, is bounded by a constant, the minimum of the function on that compact. Right? And here this epsilon depends actually only on n for divergence form operators. Taken any smaller, any number smaller than n over n minus 2. And this constant here, CWH, as we Kernack, is something which depends on the backspace, the integrability of coefficients, ellipticity, and the norms in these spaces, LQ and LP, of the coefficients of 0 and the first and 0 order coefficients of the operator, and of course of the size of the domain here, R, because I'm taking a ball. Right, here P can be Q over 2s, and remember from the C0 hypothesis. Well, this is a result that goes back to, not written in this form, but to De Giorgi, and then it was written and extended in general by Moser, by Trudinger for divergence form operators, and by Kirov and Safonov for non-divergence form operators, and Farelli and Cabret for viscosity solutions in non-linear equations, and Koike-Swish for non-unbounded coefficients. This is a quantification of the strong maximum principle, in the sense that if u is positive somewhere, then this integral is uniformly positive here. And so u is uniformly positive everywhere. So a little positivity somewhere gives uniform positivity everywhere. And in other words, this is a growth lemma in the language of regularity theory. And as such implies also Hölder regularity of solutions and Hölder bounds. Well, there's also a homogeneous version of this result. If we have a right-hand side, we have the same thing with some correcting terms, which is a Lebesgue norm of the right-hand side. Well, so the question is, can we? So question is, what is the best C actually? What is the best CWH? Right, and we also need to take a little bit care of this norm here, which usually is written like LP in the whole domain where the equation is set, where actually it is possible and necessary, in my thing, to take a norm which is essentially local, which does not increase when the size R increases. And that's why we write the following uniformly local Lebesgue spaces that are pretty common in parabolic theory. So it's just you just take the maximum of the Lebesgue norm in the domain across any possible ball with size 1. That's complex. And then let's introduce the following constant, which is going to be important. So for each, we take, let's take for an instant Q and P to be infinity, like we have bounded coefficients. Why not? So if Q and P are infinity, these constants here, beta and gamma, are just 1 and 1/2, as defined like this. And so this M is essentially like B plus square root of C in L infinity norm. Or if there are Lebesgue norms, we have to take these powers here to get the right scaling. And so it turns out that with this M, the constant in the Kernack inequality is exactly exponential of a constant which depends only on dimension of ellipticity times this m times the size of the domain. That is obvious. That this is you cannot do better is obvious. You just take a simple ODE. Its solutions behave exactly like b plus square root of c, right? Which is exactly what we have here for P and Q. So it's clear that one cannot do better, but we prove that for any operator in any dimension, we actually have that. We have that bound. Well, and there's also, again, this can be written also for non-homogeneous equation, the same optimal constant, with some right-hand side, which is in uniformly local element spaces. Well, the proof is, the idea is not difficult to explain. I mean, if one takes a ball of size 1 over m, and rescale it to a balls of size 1, the new operator has coefficients which are whose norms are smaller than 1. And so we can use the standard equality with norms smaller than 1. Then we scale back, cover with balls in an optimal way, use an optimized Harnack chain, and we essentially get this. And there's also a variation of the other side inequality, which is the so-called local maximum principle, which instead of super solutions concerns sub-solutions, and where the maximum of a function is bounded by some LP norm, or any LP norm, L epsilon. So these two together, these two inequalities together, connect supremum of U to infimum of U if we have a solution, both sub and super solution. And we get the standard inequality with this optimized constant, which is exponential of MR. Well, and this essentially, it's a little bit of work, but now if we have this result, and if we linearize a term like logarithm of U to power A for A is more than 2 in some equation, then we can see that applying this and taking into account exactly this logarithm to a power smaller or equal than 2, then the relaxation of the weak Harnack inequality gets us the strong maximum principles. That's the idea of the proof of the theorem that I quoted here in a few moments ago. Again, I don't want to spend too much time. Yeah, so there was an open problem that we now believe is being solved about extending this result, which was valid only for the model case, to the full integral Vasquez integral hypothesis. And that is the 1 over square root of primitive is divergent, has divergent integral. And we believe that, and actually it turns out that it's not possible to, we don't have a proof which is the same for divergence and non-divergence cases. We have different proofs that it's an unknown word. So skip this. Now let me move to a different looking problem, at least at first glance. That is the so-called, nowadays it's pretty trendy, the so-called Landis conjecture. And it's a question which goes back, I don't know how much actually, but to my knowledge, it appears in written form for the first time in a survey by Kondratiev and Landis in 1988, which is a very simple question. Take the Schrödinger equation, right? Just stationary solution, and with a bounded potential in, say, some exterior domain of Rn. And is it true that solutions of this equation cannot decay more quickly than exponential at infinity? In other words, is it true that for some constant, necessarily sup Sx goes to infinity of exponential mx times u, modulus of u, is strictly positive? So that very simply working question is actually still open. We don't have full answers. In particular, if one considers real solutions, which is the only thing we consider here in this talk. There are variants also of that question. There are variants of that question. We can relax. We can ask for more. Instead of asking the question to be satisfied in an exterior domain, we may ask the solution to be entire, to be defined in the Hoare space. Even for this case, the answer is still not known. There's a weaker conjecture done by Carlos Koenig, which is that there are no solutions which decay no quicker than exponential to a minus power of x, where the power is bigger than 1. This has recently been proved for n equal than 2, and even this is still open, big high dimensions. And of course, there's the question about, which is what we were mostly worried about here, about more general operators than the question. Yeah, so just an observation, if we assume complex solution in 2 dimensions, this is actually the question, the answer of this question is false. And it turns out that the optimal rate is pretty interestingly exponential of minus x to power 4/3. There are solutions which decay like this. That is super exponential. And this has been a field into which there's been important developments using essentially Kahneman type estimates. Since they are valid for complex solutions too, they couldn't be used for the conjecture in the real case, which people believe should be true, but are not able to prove by this point. So there was a search in recent years following the work by Carlos Koenig with Silvestri and Zhiwang in 2015, in which they proved the weak form and the conjecture in 2 dimensions, the sum additional hypothesis on the coefficients. And they proved that for each sphere x equal to r, the U decays at least like exponential of minus r log r, or r log r square in exterior domains. This paper has been generalized in various dimensions. But all works were for 2 dimensions and equations in divergence form under the hypothesis, which is nowadays pretty almost always used, that we make the supplementary assumption that the coefficients are such that the operator satisfies the maximum principle on bounded subdomains Rn, or of the exterior domain that we are given. Essentially, this is like the first eigenvalue of the operator is positive. Luca-Rossi proved the result in any dimension for operators with bounded coefficients in non-divergent form by using comparison arguments and the fact that if coefficients are bounded, then some negative exponential is a subsolution. There are also other results like probability and duality. The only result that avoids this hypothesis of maximum principle on bounded subdomains, positivity of first eigenvalue, is a recent work by Malinnikova, Nadirashvili, and Fyodor Nazarov, which actually says that the Koenig's form of the conjecture is valid, and even that the decay is no worse than exponential of minus x square root of log x. This uses a really 2-dimensional method, so higher dimensions is still. What we contributed to this by applying the optimal form of the constant in the Harnack inequality is that the conjecture is valid under the hypothesis of maximum principle, but for operators with unbounded Warren coefficients. Really, which is essentially an open problem. Yeah, so the result is essentially, even we actually prove that if we have a solution, let's say in Rn, then the supremum of that solution in each sphere is bigger than this negative exponential, which is exactly like exponential minus r multiplied by this, again, this m quantity, which is like b plus square root of c if bounded coefficients, or b to some power plus c to some power, which is the right scale if they are only in some Elliptic spaces. And again, this is a consequence of the optimal hierarchy. So yeah, this is essentially the idea of proof is compare a given solution U by a solution that you can by a positive solution that you can construct and to which you can apply the optimized Hallan inequality. And so the optimized Hallan inequality gives exactly exponential, as we saw. Yep. Let me observe that this result here, a result of this form, that the supremum over spheres is bounded below by an negative exponential, does in fact require that the first eigenvalues be positive. They are counterexamples to solutions for these that oscillate and so get power zero, that get value zeros on something. And such these operators have negative eigenvalues. Okay, so to summarize this, this is a work of mine and Philippe Souple 2 years ago. So we have an approach which is based on the weak and the full Harnack inequalities with optimal dependence of the constants in the lower order terms in the equation with the size of the domain, and that treatment, that approach unifies the treatment of these two classical problems, the Vasquez strong maximum principle and the Landis conjecture. And essentially it unifies them and gives results for operators with unbounded coefficients in situations where all previous results actually require unbounded coefficients. And it provides quite short proofs and treats simultaneously equations in divergence and non-divergence form. And in particular, and also it has these extensions to well, what I would like to do now in the remaining time is to speak of actually a further development further question on the Landis conjecture, which actually leads to considering optimal constants in other, in a sense, even more basic elliptic estimates, such as the generalized maximum. So let me show you a recent result by Kevin Lubalk, which is also based on a method by Michel Pierre. It's the following equation. It's a specific equation. Let's take this divergence form equation, right? With bounded coefficients and negative zero over the term. Then they could prove that actually a stronger result than one I showed you. I showed you a supremum of U over each sphere is bigger than negative exponential. They can actually prove that not just supremum of U, but even the average of U on each sphere is bounded below by a negative exponential. Let's recall this M is always the B to norm of B to a right power plus norm of C to a right power. So it has several ingredients, this result. It has several ingredients, but the most important one is actually, which is very important per se, is an optimized C1 bound for solutions of the Dirichlet problem for the operator Laplacian plus B dot plus C, B dot gradient plus C. So this is a standard both divergence and non-divergence form equation with the Laplacian operator. And assuming that coefficients are bounded and the operator is standardly coercive in the sense that the zero order term is negative, then solutions of the Dirichlet problem are such, this is very well known that for this Dirichlet problem, there is L infinity and C1 bound for solutions. So we can bound the gradient, the solution and the gradient by constant times the right-hand side. And it is actually possible that what I proved is that this constant can be optimized to precisely again this exponential for that equation. And once we have this, essentially this result on the Landis conjecture is obtained by duality. You multiply by a well-chosen eigenfunction in a domain, integrate by parts, and you can use this for boundary to estimate boundary terms. So it's actually this result that's important. Once more, the same C1 bound with optimized constants. And well, the first proof of this theorem was complicated a little bit. And one of its ingredients, it uses even tools such as doubling the variables, which are very typical for C1 estimates. Also another important ingredient that proof was a result by Koenig, Silvestri, and Wang, and generalized by Koenig and Lubov in all dimensions, which is logarithmic gradient bound. It says the following: if we have a positive solution of the equation with zero, the homogeneous equation, again bounded coefficients, then we can it is known that we can bound the gradient of the function by the function itself. But if we divide the gradient by the function, note that it is expected that both the gradient and the function can grow as exponential of them. But if we divide by the other, there's a cancellation. And so actually this supremum is not exponential of m, but it is linear in m. It is bounded linearly in this quantity m, which is, I recall again, is norm of b plus norm of c to the right powers. Right, no, it's not an exponent. Each of the two, the numerator and denominator here are exponentially, but if you divide one by the other, they cancel to a linear. Okay. Well, actually, the gradient bound itself also admits a simple proof. It is not difficult to optimize first the C1 to C0 estimate in terms of m. Actually, it is possible, not too difficult to prove that. We can prove we can show that the maximum of the gradient of such an equation, solution of such equation is like m times the maximum of the function itself. And if we know that we have here an equation in non-divergence form too, there is a very classical result by Alexandrov and Bakelman, the so-called Alexandrov-Bakelman-Pucci estimate, or ABP estimate, which for such equation tells you that the supremum, this supremum here on the right-hand side in this inequality, is controlled by a Lebesgue norm of f and exponential times exactly Lebesgue norm of the coefficient b. So combining these two essentially gets the gradient bound in this form over here. The supreme in here. So now, okay, but that used the ABP estimate, and the ABP estimate is a non-divergence form equation result. So one may wonder, and what if the operator is only in divergence form? Then can we do this? Well, actually, the ABP estimate has its counterpart in the divergence framework. This goes back to Stampakian. Probably it was written in full generality by Schrödinger. And it says what we nowadays find very normal, that it says that if we have a solution of a Dirichlet problem, let's say in some domain, here I'm taking both, right? And if the domain is rightly coercive, for instance, the zero order term of this operator is negative in distributional sense, then the maximum of the function, this is not u, this should be v here, this v in the solution here, is controlled by a constant times some Lebesgue norm of the right-hand side. Again, this q is bigger than n over 2. But Actually, a question which surprisingly has not been considered is what is the optimal dependence of C and in the Lebesgue norms of the coefficients dc and dr. So that's what we wanted to look at, which in particular would give this extension of the line, this conjecture, but obviously it's a very interesting question itself. And well, first thing, of course, is to check what the known results give for the constant in the Stampacchia-Truding inequality. So let's write it for a particular case, take divergence just the first order term B. Then, if we examine the proofs of this theorem, there are actually two proofs, but they lead to more or less the same type of result by Stampacchia, based on the George cutting, and by Moser-Trudinger, based on iteration, Sobolev inequality and iteration. So we get that the constant, the dependence of the constant in B, in a normal B, is exponential to B to a power, okay, and that power is something that's bigger than 2. This comes from the proofs that everybody knows. While, for instance, for the non-divergence case, when there was this ABP inequality, we know that there we get sigma equal to 1. So one would expect sigma equal to 1. In a work to appear with Philip, we actually prove that this is true. Sigma can be 1. Sigma is 1. Yeah, I mean, this is the optimal constant is really this constant here with sigma equal to 1. We even prove a Lipschitz estimate, provided we assume that the zero order coefficient is at least order. So essentially, the main the leading order coefficients are the sort that allows C1 estimates. We do not know if this can be removed. Let me give here. Well, this is really a full theorem. So if we assume that we have some uniform coercivity, but let's forget this one, the one here. I mean, essentially we have this bound here. It's exactly the one that's expected. So if we have a sub-solution, it is bounded above by a constant times the distance to the boundary, and the constant is precisely exponential of MR. Under a condition a little bit of a uniform, which is unavoidable, some sort of uniform coercivity of the operator. And this implies for the Dirichlet problem that there is the gradient bound for the full equation, right? No particular cases, also unbounded coefficients, that we have the gradient bound. C1 alpha bound with the right constant. And so we can extend the generalized Landis result to arbitrary operators, as long as this is true. Well, again, the proof is by duality. We used another result here, which is a sort of a boundary Harnack inequality, which is another line of research we've been considering. And the result I obtained with 2 students says the following. So it's like a Harnack inequality or weak Harnack inequality, but up to the boundary in a domain. Then essentially we have the same sort of result, but provided we replace the function by the fraction, of the function and the distance to the boundary. So instead of in the usual Harnack inequality, we have a compact subset, and then of course the integral and the infimum of the function itself. Here we go up to the boundary of the full set, and we have to pay by putting u over the distance. But with this result and the duality, we have, of course, some supplementary work, which is trivial, we can only mention both. Okay, and then once you realize that such boundary results here hold, such as infimum of u over distance is bigger than something positive. This is actually this result here, this inequality here, this boundary Harnack inequality is sort of a uniform Hopf lemma. And there's another uniform variant of Hopf lemma, which is so-called Morrow-Ostwald inequality, which became very well known after work by Brisis and Cabaret of 30 years ago, which says that if we have a positive super solution of an equation with positive right-hand side, then U over D is bounded by a constant A1D norm of the right-hand side. It's being used in various contexts. What we can do with our method is actually to extend this to arbitrary second-order operators, and above all, to give the optimal constant in this inequality again, which is again the same expression. Right. So that's and also we can extend this result that I quoted on the logarithmic gradient inequality to arbitrary operators. So since we started a little bit earlier, I should finish a little bit earlier. And so I'm going to stop here and say thank you.
So thank you very much for your nice talk. Let's ask the audience if they have questions or comments. So please, are there any questions? As usual, you can, yes, you can use your microphones on and also on the chat as you prefer. No, are there any questions? Just a curiosity. Can you get some result for non-linear problems?
Yes, for non-linear, such as using, for instance, as at some point I probably quoted some sorts of non-linear equations here, such as, for instance, maximum minima of linear operators, so-called Hamilton-Jacobi-Bellman operators. We have results. So essentially, most of these results extend to such type of operators. And of course, we have these results here, which also have non-linearities with respect to the unknown function. Yeah, so there are some extensions to non.
Okay, but function f could only depend on the u,
no, you can depend. Yeah, there's also extensions of these things. One can, we would expect that under the right hypothesis, we can put also dependence on the gradient.
Okay.
But this has not been done.
Okay.
But
okay.
most probably is good.
Okay, thank you very much. Other questions? Comments? So if not, thank you very much for being with us, and yes, we hope to see you in the next seminars. Thank you.
Thank you so much. Thank you so much, and thank you again for organizing this.